It's a real pleasure to be here. I'm Pierre W4CKX. I've got a slide to introduce myself. Thank you for coming. I really appreciate you being here. And I'll start with a piece of trivia. Where were you in 1971? So 1971 was Mariner 9 mission to Mars, and that's the lander that was sent that year. And you're going to say, what does it has to do with Ribbit? So stay with me until the end of the presentation, and then we'll answer that trivia question. So we have 30-minute presentation in front of us. So I'll highlight, why we're doing Ribbit, how we do it, and we'll reveal the secret sauce. This is a new content that's not been published online yet, so I will share with you the mode and the structure, how we implement it. That becomes a little bit technical, but I know some of you will like to dig into the details. And at the end, everybody gets a free giveaway app with your tech demo, so you can actually use Ribbit at home for free. And plenty of time for Q&A. So what is Ribbit? Ribbit is a new digital text messaging mode that works on HF, VHF, UHF. You could also use this on SHF, but not much equipment there. And it's for both recreational and emergency use. And the benefit is that it increases the density of information you transmitted on the spectrum you use. So voice is not really efficient use of the spectrum, and we can actually convey much more data every minute by going through that text messaging mode. And what we do is we use the modern smartphone, which is extremely powerful computer in your pocket, and we use principle of software-defined radio, which is modern developments, to actually take things that would requires transistor gates, resistors, and capacitors on very expensive analog circuit, and we actually do everything into software in your smartphone with no equipment. So you take any handy talkie, and that could be an analog HT or a digital HT, and you use the analog mode. And you can use that HT with your smartphone with no hardware. So no TNC, no cable, no nothing, no spend, $0. Download the app and get it, use it right away. And the benefit of that is that it's distributed, because every single ham can have Ribbit in their pocket on their phone. And so if you would be in an emergency and there's no internet connectivity, then this is when Ribbit starts to shine, because it can actually function with no internet. And Ribbit, and we're very proud of this, is open source, and so everything is published, and it's in early stage of development. So a little bit about me. So in the introduction, he went over this, but I got my first license in '98. I was graduated from high school, first year in university, studying physics, and some Elmers came to me and said, you know what, son, you'd better do your test right now, because the test is very difficult in France. I don't know why they do that, but it's almost like the harder they can make the test, the prouder they are of their license, but then they damage the membership. So, and it hasn't gotten even better over the years. So they said, well, you're studying physics, that's the best moment to pass your exam. And they were absolutely right, yes? Yes, so actually what happened is, I didn't renew the call sign with the government after a few years, like 2-3 years, because I didn't pay the annual fee after the year 2. So it got dropped. But the thing is, the block allocation in F4 is so wide compared to the French population that they never had to reharvest the call sign. So in 2020, in the middle of COVID, I said, I wonder if I still have my call sign. So I called the equivalent of the FCC in France, and I say, can I have my call sign back? He said, well, do you have your exam certificate? I say, no. Well, you need to first ask for your exam certificate to be reassured. I said, well, how do I do that? He said, well, just fill that paper. So I filed it. They sent me a copy of the fact I passed the exam back in the day. it was still valid. Then I turned around, and then I said, well, I'd like to reinstate my license. So that was just paperwork. But I kept it. So I met my wife at Georgia Tech and moved permanently to Gwinnett my 16 years ago in 2007. Our first home was in Snellville, and the last 8 years I've been in Sugar Hill, close to Bob, actually, near neighbors. And been fairly busy with 2 kids, and when you're young in your career, climbing the ladder, typical stuff. But during the COVID, a lot of us were home and we're looking at, hobbies and stuff to do and thinking about it. So I rejoined the hobby. I passed my general on the first, technician and general on the same sitting. And then I asked the FCC for a vanity call sign so that I could have, W4CKX. And I'm very happy to have matching call signs. My interest to come back was emergency communications, and we're going to talk about it. To accelerate the concept of Ribbit, I actually found tremendous support in the Open Research Institute, and I'll present what it is. So I joined in 2022, and that's when everything started for Ribbit last year. So the Open Research Institute, what it is, it's a non-profit research and development organization which provides all of its works to the general public under principles of open source and open access to research. So their focus is on ham radio, open source. You can go look at what they do. It's really, really high level on the technical side. Their aim is to develop an entire stack to have soon geosynchronous satellite in orbit with 100 voice channel digital over the US. So I think they're about 5 to 6 years away from reaching that milestone, but they're developing groundbreaking technologies at the ORI. And so ever since I joined ORI last summer, I actually got in contact with Ahmet Inan from Germany, who was working and doing some research at the ORI, and Ahmet is behind 99% of the codec of Ribbit. So I came in with the user, the use case, and the constraint, and then he came up with an implementation to make it work. And then Jason stepped forward and helped us with the web, so we have a nice looking website, so that's thanks to Jason. If you're interested to know more about Ribbit at any point in time, you can find us at ribbitradio.org. I'm going to take the opportunity to just showcase a bit the website. And all assets of Ribbit are owned by the Open Research Institute, which is a nonprofit, so we're able to raise funds and be tax deductible. So on the website, you'll find what it is about. So does it look good on the TV? Yeah, it's pretty good. It works on your cell phone too. So it explains digital messaging with no hardware, open source, and then you're going to see our very first poster, which is a scientific poster to explain the concept at DEF CON in August 2022, and you had a lot of the feds were there and they looked at it in detail, so that's where we kind of came in the open and said we're going to do that. And then we did a presentation in September 2022 at QSO Today. I think we got about 10,000 views from that conference online. We also were featured months later in Red Pack, which is focused on MCOM. I think we're the second most viewed video in the Red Pack archive. And then we started to get attention from YouTubers. So this gentleman from Switzerland did a wonderful video to explain how it works, so we're going to play it later. Here's a demo of how the app works by Ahmet himself. And then later here, if you want to be informed, I would recommend that you join the announcement mailing list, because anytime we got a milestone update, like new feature on the app or things happening, we'll broadcast to the Ribbit announcement mailing list. Here's the links where you can download the app, and then down there you got a user community mailing list where user can actually exchange information like how you do this or that. And then we also have a developer mailing list for the people who want access to the source code or contribute to the development. That's pretty much it. And we've got a donate link because we're hosted under a nonprofit, and we've actually, with not much request, we already raised $1,000 without even asking people to donate. So it just happened in the background. All right, so I'm going to cover why we do it. So there wouldn't be Ribbit without cellular communication. So the brand new concept behind it is your cell phone is the most advanced piece of communication equipment that a citizen will have access to. So the military, they got their own comms. First responders, they've got really good equipment as well. But for a citizen, we rely on a cell phone and a cell tower. And this is the default mode of communication for us. It has the fastest connectivity, the user experience is really good, and there's lots of modes inside the cell phone. You can do web search, email, chat, text, phone call, video call, sharing pictures. It's really rich, and it's best in class. However, it's a single point of failure, and it's going to work really great 99.5% of the time, no question about that. However, in less than 1% emergency case, cellular can go down for weeks. So what happens is that infrastructure can fail, and then when it does, you have a large population without communication for weeks. So we see that like during Hurricane Katrina, we had about 1,000 cell towers were knocked out during that hurricane. So that was like GSM, early days. We also had in 2017, or no, that's a little bit earlier than that. In Hurricane Maria, they had 360 cell tower, about 75% of Puerto Rico's cellular network going down for about 2 months. More recently, the wildfire in California, what happened is the cell towers, they're connected to the backbone with fiber optics, and when the tree starts to, embrace and engulf, well, what's on your telephone poles? You got the power lines, and right below you got the fiber optics, and they melt. So they had 57% of Marin County shut down, 900 cell sites not operating. And that was a year before I was presenting in 2022. So about 2 years ago, in Kentucky, in the trace where the tornadoes were passing by, knocked down the cell tower, and they just forecast that it would take a month and a half to fix most cell towers. So what happened is, when that happened, you got the crews, they're going to fix that cell tower as fast as they can, but it just doesn't happen in a blink. It can take a few weeks for them to actually fix it. The more towers are down, the longer it's going to take for them to fix it. So what usually happens? Well, we step forward, and that's who we are. Through RACES and ARIS, operators step on the air, and they help assist with communication. And it works really well for a short period of time, like several hours, a few days. And it becomes harder to sustain over days and weeks because you're going to have lots of things going in the way, like maintaining the flow of communication with hundreds of people over a long period of time is challenging. You need to overcome operator fatigue, handling numerous concurrent subject and issues, remembering earlier subjects, so you have to have a sort of memory over time, transcribe everything in writing, transferring the context and information to the next operator, sharing the workload among different operators, and also communicating exact location of asset and message provenance. And all that needs to be done over the air by voice. So we see that VHF and UHF voice mode has some limitation. It takes a lot of effort to get that information going through. So what can we do to support these people? Well, we can provide them with modern text messaging capabilities. And we provide these capabilities to work on the exact same voice communication infrastructure that they're using. So same frequency, same repeaters, and we can send text message completely complementary to voice. And what you can do is you can start talking, say, hey, Joe, I'm going to send you my local report. Then you type it in Ribbit, transmit it, and they receive it digitally on the other side, and they acknowledge they've received the entire content. And the benefit is you got real-time technical awareness of what's going on. all your messages are timestamped, geocoded, so you know the origin. And you can also do history and forward. And the message doesn't change over time. You can just retransmit and repeat the message forward. And it requires no additional hardware. It's just an app. So text can do more. And so I'm going to go over the benefits of Ribbit over VHF, UHF. And so I was explaining, it's on the same frequency. You don't need to use that digital mode on the specific channel. Just use the channel that's open. And so you get high-level view of all of the message, geolocation, ability to copy-paste, so there's no transcription error. You can share workload across multiple operators. You got complete history. You can respond to a message, and it only takes 1 second to transmit. So how do we do it? I mean, this looks like almost too good to be true. So what we do is we use the cell phone. Even without cellular connectivity, you still inherit a large screen, a touch interface, the keyboard input, so we leverage that. We use the compute power, which is extremely fast. Like these days, the processor on your cell phones are multiple gigahertz. Large memory, and then we also can pick up the exact time and the exact location through the GPS receiver. And of course, you got the speaker and the microphone. And then we combine that with any handy-talkie, so just an analog transceiver. Vox mode, you can use it, you don't have to. And we focus on the speaker and microphone, and we target the lowest common denominator between the two pieces of equipment, which is acoustic coupling. And by using just audio between the two, there's no hardware required. Like, it's possible for quality of life to use a little APRS cable, so then you can pipe the audio between the cell phone if you got a jack and your Kenwood connector on your HT, but it's not required. So if you're in an emergency and you don't have your cable, it's still gonna work. And to be able to get effective acoustic coupling, we had to do tremendous computation on the cell phone side to account for lots of things. Echo, drifting of the core frequency, noise canceling, detection of digital packets between the ambient audio nodes. There's lots of digital signal processing, software-defined radio happening on the cell phone side. So I've got that gentleman in Switzerland that actually explained how it works, and he worked with Amit to really dig into it. And what I'm just going to say is the name of our tech demo was Rattlegram, and the reason we didn't call the tech demo Ribbit is because the App Store was not set up on the ORI to launch Ribbit yet, and we didn't want it to create a piece of software that then would have been transferring ownership. So our tech demo is called Rattlegram, and then I'm going to try to get that to run, and I'm going to put the microphone next to my speaker, and we're going to try that out.
Phones transmits data using our radio's microphones and loudspeakers, with more than double the speed of APRS. How is this possible without cables to the handheld? And what is the relation of this project with Wi-Fi, 4G and 5G? Stay with me, I will tell you an interesting story. Hello wireless enthusiasts. Here is the channel with a strange Swiss distortion in the signal, with a new video around wireless and other exciting stuff. Make sure you subscribe if you do not want to miss the following emissions. I found this app in Steve Stroh's Zero Retries newsletter, which covers digital ham radio topics. And Ahmed, the German-based inventor of Rattlegram, helped me understand this complex topic. Let's look at how Rattlegram works. I open the app and type a text into my smartphone. The same app on the second smartphone is in listening mode. Both are connected via two 70cm handhelds. Now I hit the PTT on one walkie-talkie and press transmit on the app. We hear a short signal and the text is already readable on the second smartphone. I prepared a message just for you. Who is the first to decode it and write it in the comments? You can argue we had digital modes since 1980. What is new about this app? The first thing, its raw transfer speed is around 2800 bit per second, with a bandwidth of 1600 Hz. Pretty fast. APRS usually is 1200 bit per second. The second is that we do not need a cable to connect the walkie-talkies. It also works with PMR or GPRS handhelds, or, as you saw before, on YouTube. And third, and most important, it uses orthogonal frequency division multiplexing or OFDM modulation, which is the hottest modulation of our time. Wi-Fi, 4G and 5G protocols all use this modulation. So I thought we, as wireless enthusiasts, should understand it. Unfortunately, it is a bit more complex than just amplitude modulation. But I propose a joint journey from amplitude modulation to OFDM with stops at interesting points like FM, SSB, FSK, etc. In future videos we will build a transmitter and a receiver for each modulation to play with. But because we live in modern times, we will use GNU radio instead of transistors, resistors, capacitors and inductors. Like that, all of us can participate without additional cost. And if you do it right, our software devices should be able to interact with our real-world gear. What do you think? Will you join? And which modulation interests you? Coming back to the topic, the most pressing questions are, of course, why is OFDM so widely used? And what is the difference between our well-known modulations and OFDM? Before we even start, we have to introduce the concept of a symbol. In FSK, for example, each bit is a symbol because a symbol only carries one bit. As we will later see, modern modulations carry many more bits per symbol. The first problem OFDM attacks is reflections. We all know that our signals often do not travel straight from the transmitter to the receiver. Often the signal is reflected on walls or mountains, or in the ionosphere. Because they have to travel a longer distance, the reflected signals arrive later at the receiver. Why is this a problem? Let's assume we want to build a 2800 bits per second channel using FSK. At that speed, each symbol is 357 microseconds long. Let's assume a reflected sound signal has to travel only 10 centimeters longer than the direct signal. Because sound travels at around 330 meters per second, this signal arrives 300 microseconds later at the receiver. Sounds like not a big problem, right? Let's look at what happens at the receiver. This is the original signal and here is the delayed one. The receiver adds both because they are on the same frequency. So the delayed signal can disturb the next symbol. Not good. It gets even worse with a strong reflection or several reflections. So what to do? One possibility is to add a gap of 300 microseconds between the symbols. Then the delayed signal would not disturb the next symbol anymore. But we would lose 50% of our channel capacity because it would lead to a lower bit rate. The same applies to radio waves. Because the speed of light is much faster, the effect is only on higher data rates. Still, current Wi-Fi and mobile phones easily reach such rates. Fortunately, clever guys found a simple solution. They divide the available bandwidth into many small channels. Because these channels are much narrower, they do not allow high data rates, but their capacities add up. They call their invention OFDM. Now we already know the meaning of frequency division multiplexing. Hams who know FT4 or FT8 know this part of OFDM. In FT4 and FT8 we see a lot of parallel information streams on one 3 kHz SSB channel. Each FT8 stream has only a 50 Hz bandwidth. Rattlegram goes much further and uses 256 parallel streams. Each stream has a bandwidth of only 6.25 Hz. To get the same throughput, we can reduce each stream's speed by 256. Exactly what we need. One symbol in Rattlegram is 180 milliseconds long. So the 0.3 milliseconds delay only disturbs the next symbol for a short time. If we added a short delay after each symbol, the delayed signal would not hurt at all. Very clever. Rattlegram invests 20 of the 180 milliseconds for this protection. That is what I call a plan. Divide the available bandwidth into 256 tiny parallel channels. Reduce the symbol rate of these channels and add a short delay between the symbols. All our problems are solved, right? Right, but we created new problems. Did you ever see a filter with 6.25 Hz bandwidth? And how big and expensive would it be? And what about 256 of them? And what about channel separation? We all know that if we have two strong signals nearby, it is hard to distinguish between them. So this idea seems to be good in theory. Must have been a physicist or a mathematician who invented it. An engineer would never have such stupid ideas, right? Right until the software-defined radio was invented. Then things changed, as Rattlegram shows. Mathematicians found a formula that creates many parallel channels that do not disturb adjacent channels. What is impossible in our analog world is possible in mathematics. This is where the orthogonal comes from, by the way. They use synchronized designer signals particularly created for that purpose. Orthogonal signals do not disturb adjacent channels. In FT8, each channel belongs to a different station, which cannot be synchronized. This is why it needs broader channels. This formula is called inverse Fourier transform. It creates values that, if sent to a digital-to-analog converter, become a signal that can drive a loudspeaker. I call it black magic. They call it an OFDM encoder. On the receiver side, they use an analog-to-digital converter and use what they call the inverse function, which, as an output, gives us back the 256 parallel signals. Cool! Without one capacitor or inductor. And with a bandwidth of only 6.25 Hz per channel. Incredible for an analog guy like me. We still have an enemy to conquer. Noise. If we have weak signals, it is easily possible that a few of the many bits are disturbed, and the received data is different from the one sent. This is not acceptable in digital signals. So, what to do? From earlier days, we know a simple trick called parity. We added a bit at the end of each byte, calculated from the bits before. If one bit was disturbed, the receiver could detect it and knew something is wrong. I cannot trust the received data. But it did not know where the error was. Not very valuable for a system like Rattlegram, where we have no back channel to ask for retransmission. In the past, we had situations without a back channel too. Transmitters were used to transmit confidential data to spies in other countries. They obviously did not have a transmitter to request a repetition of data with a parity error, because they did not want to be caught. So we used forward error correction, or FEC, where more redundancy was added. Like that, the receiver was not only able to detect disturbed messages, it also was able to rebuild them. LoRaWAN, by the way, uses the same principle for sensors without the back channel. Of course, FEC, or redundancy, also reduces a channel's throughput. But it is necessary for noisy channels. OFDM has another ace in its sleeve. Ahmed uses QPSK, which can transmit 2 bits in one subchannel. As we all know, FSK can only transmit 1 bit per symbol. Wi-Fi and other modern systems use even more potent schemes called quadrature amplitude modulation, or QAM. They go up to 6 bits per subchannel. You can imagine how fast such channels are. And because of the increased throughput the many parallel channels provide, we can sacrifice a part of the additional speed for transmission reliability. Because Rattlegram has no backchannel to ask for retransmission, Ahmed decided to add 50% of redundancy. Summarized, with Rattlegram we can study this fundamental protocol and do some experiments. And because it uses acoustics with low speed of sound, we see all the effects already at low speed signals. This has the significant advantage of using cheap instruments for our experiments. And we can try to optimize the protocol for performance on our standard channels by extending the bandwidth or adding a backchannel. And with a backchannel we probably could use higher order QAM to boost speed on our connections. What do you think? And do you know of ham radio protocols using OFDM? That is all for today. As always, you find all the relevant links in the description. 73 to everybody, and please consider supporting the channel by using the links in the description.
Thank you. So, questions, maybe, up to now? LoRaWAN? Yeah, so LoRa, they have sensors and they do send their message in one way. And so we're in the same technology era as LoRaWAN, yeah. We got, I don't think Vara has systematic polar code, forward error correction to it, or just QAM, yeah. Right. Do you need equipment? Yeah. Right. Right. So that's right. In the early days of analog modems that would go over your phone line, when they went from 300 baud, 9600, 1440, 14,400, and then 56K, you had that, you know, research around how can I encode the most bit per second over audio. One thing that it didn't have to deal with was the multipass reflection, because they had the benefit to be directly coupled on the audio line, so you wouldn't have the multipass rejection that we need to take care of. And the second thing that they wouldn't have to deal with, which Ribbit is implementing, is because we're listening to the ambient sound, you could have background noise from anything around it. So on Ribbit app right now, on the demo, when you put your spectrum analyzer, every time you speak, you see your voice over it, and then the signal processing needs to filter out and find the digital packet in the ambient noise. So you got all that like searching for it. Whereas on the modem back in the 90s, when you were not transmitting packet, you only have a background static noise on the line, but your signal to noise ratio would probably be more pronounced and not as like you know, weak signals that we're working on. But you're right. I mean, it's similar. We're taking some concept from back then, and then we're baking in the newer concepts from like 4G, 5G, and Wi-Fi. So it's a blend of old and new. Yeah, in fully software form on your cell phone, yeah. Yeah. Yeah, somebody needs to be on the other side. So there's no need for an infrastructure. So who's going to use this most? So there's two big use cases. There's recreational, which will come later. So we foresee people doing Summit on the Air, Ribbit, and Parks on the Air, Ribbit. Why they would do that? Because then in 1 second you got your entire packet of to, from, geolocated. So all of that data can start to be much more automated in terms of like your achievements of how many parks you activate. And then you can't cheat because you got the physical GPS log of exactly where you were. So yes, you were on the summit, you were not in the parking uh, parking lot. And the second thing is that if everybody's played with FT8, at one point they'll realize that if they can do a QSO in 1 second, I expect at one point contesting is going to start to go crazy with Ribbit. Now, it's not going to transmit over weak signals as low as FT8 can do, but if your propagation and bond conditions are good, you should be able to log hundreds of QSOs in no time compared to FT8. So I expect at one point it's going to flare up. So that's on the recreational side. On the emergency communication side, we enter the next 2 years. We're in hypercare with an audience which is Races and ARS group. I had the ARL contacting me. They're very interested in what we're doing. So at one point, probably in about 2 years when it's matured, we'll be able to have a toolkit. And what I want is people that work in emergency response, like could be volunteers, could be the Red Cross. What happened is they can be in a shelter and they can start, doing survey of data, and it's much more efficient to do it in a text form that just go over the audio. So they'll have the Ribbit app pre-installed. Part of your ARS group preparedness will be make sure you have your Ribbit app installed on your phone. Yeah. Right. So we implement, yeah. So it'll be on it. We'll have the form baked in, yeah. So it'll be the template, but we need to kind of reinvent the form. So I started discussing how we can do that because we don't really want to host like the print perfect PDF version on your cell phone and try to transmit the PDF over. That wouldn't be efficient. So what we're going to do, we're going to recreate the form in a cell phone user interface because you need to have the UX to be very streamlined so you can use your thumbs, but it's going to be the same content, which is going to be to, from, timestamp, who signs it. We'll send it over. The good thing is once you compose the form on the message, there's a non-tamper, so you can re-forward it, but you can't tamper the form. And we'll have the credential signatures as well. So at the tail end, when they're in the command center, we'll have, I hope in 2 years, we'll have the desktop version of Ribbit. And then for them, it's going to be like a triage. They'll have all the message. They can sort them by priority. And then they can extract the form and print them out if they want them on paper log. Yeah. Right. 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 Yeah. Our goal is to make these groups of volunteers have the most modern tool that they can have, and so make their life easier. Yeah. Oh, plenty of question.
Yeah. Do you see this being integrated into something like a flex radio, for instance? In other words, replacing the...
Not initially. I guess if the contesters would love it, then I'm pretty sure Flex could implement it because they got this touchscreen interface and they got enough processing power to run it on the Flex. Yeah.
the flex.
RF1 Finder also, these high-end handy-talkie that are touchscreen,
I know, but
they could do it too. Yeah.
You've got the API on the Flex has an API basically for the desktop. So if you can get into your Flex with the API, then
it's open source, and so we would
Yeah.
be happy to help them implement them on the Flex.
You have a question? Coming around.
All right. I kind of tested where I transmitted something, and where does it go? Because I couldn't find somebody to receive that message.
There's one right here. So you can do
So
audio.
what did you get? Oh,
Try it
They're
again.
going to do a test.
Actually, I have two questions here. In the About box of the Rattlegram application on Android, it says a prolonged exposure to the ultrasonic sounds.
Okay, I'll explain that. Yeah.
Do I have to worry about my dog?
No. So that's only when you use, so on this, because in this test demo, we open up all of the parameters to the codec. So if you stay on the 1600 bandwidth, you don't go into like high bandwidth, 48 kilohertz bandwidth, it's not going to go into high frequencies. I'll show you on your phone with which setting is going to go into ultrasound. But in the Ribbit app, we take all that away. We already know which modes and configurations are the most efficient, so there'll be none of that complexity. Yeah.
This is also probably the right time to plug the workshop.
Yeah. So next weekend is the workshop, so you can install the app, bring your HTs, and we'll have we'll transmit messages, and I'll answer all questions and until everybody can figure it out and get going. Yep.
Actually, I want to go.
So DMR is going to destroy the signal. Because of the TDMA, it's going to chop it. Like it's kind of like going through a cheese grater. It's going to remove 50%. It's so shredded at the end, there's nothing that's left. Yeah. One more.
Last one here. As a software developer myself, it would be nice if you would consider including an API for people to provide plugins, because this looks like this is going to catch a lot of attention in time.
Yeah, yeah. We'll meet there. If you want, you can compose a message and send it over the microphone, and then the other phone will pick it up. And then we'll take a question right there. And then I've got lots more to present.
I'm typing it out.
Yeah. Whether it's a short message or a long message, you need to have the entire. Send it again, because you didn't send you put it on the microphone halfway through the message.
Okay.
You got it?
Oh, you got it? He got it. Okay.
Remove your fancy header.
So you're using acoustic coupling between the HT and the
If you had a cable, could you use the cable and increase the performance, the put through, and not have to listen to it all?
So the easiest quality of life improvement you can have is use So one of the quality of life improvement that you could use is an APRS cable, and that's if your phone has a 3.5 millimeter jack, and then you got the Kenwood connector, that would work just fine, and you would reduce back ambient noise, so you would increase your transmission success rate. The second thing though is that if you leave your HT in Vox mode, every time you get a notification on your cell phone, you start to broadcast that. So bing, chime, 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 chime on the frequency. So we need to work a little bit on the operating system to filter out all of these, operating system notification chimes so that we don't broadcast them. And modern phones do not have 3.5 millimeter jack, so we need to work.
One other question quickly.
Yeah.
Everywhere I've seen it, it says smartphone, so I don't know if it will work with my iPhone.
Yeah.
that's a smartphone. What are you talking about?
So So for phones that don't have the 3.5 millimeter jack, you can have an adapter. The thing is, in emergency, you might not have it. So we need to be able to really, use the least amount of gear possible.
So, question here.
Yep.
Maybe this is piggybacking off the gentleman who asked about APIs. Do you foresee a time when you could send things beyond just text message? Because you could send any information, pictures
Right.
or whatever.
So when it comes to information density, text message is the sweet spot because we're able to send, so currently 170 bytes. So in the new Ribbit, and I'll show that in the next slide soon, 256 bytes in 1 second. If you start sending image, you're gonna have your transmission going on for minutes, and then you kind of like block the air and congest the air. So yeah, so CSV file for so Ribbit will implement how do you call that, spreadsheets, but it's gonna be its own format of spreadsheet. I've got a slide on that. So at the Q&A, I'll put that on the screen for spreadsheets.
So I was wondering if you could connect your cell phone to your radio via Bluetooth. Does the app use Bluetooth connectivity?
Yeah, so we covered the technical. So here's the most important thing. So on AM, FM, and single sideband, it works straight through. DMR, it doesn't work, but that's where you need to use your DMR radio in analog mode. And it survives Bluetooth audio compression and YouTube audio compression. The problem with Bluetooth is that there's no standardized profile for radio. So if we roll back into 1997, when they first started Bluetooth, at the Bluetooth SIG, they define profiles, and that is very much the behavior of how the device should behave on the Bluetooth ecosystem. There's a profile for headset, these headsets we had in 1998. There's profile for dashboard of your car, profile for cell phone, profile for audio speaker with or without microphone. There's no profile for HD. And what we would want to is to go at the Bluetooth SIG and say, hey, we need to create a profile so that we can share it to the manufacturer. And what we want is we want the oldest audio profile, which is stereo mic and audio, with one added feature, which is a data link that tells the receiver on the other side whether PTT is pushed or not. And that PTT logical line is not encoding in any profile right now. And the problem is Bluetooth is not open source or open standard, so to be at the Bluetooth, you need to pay a huge membership. So the only way we get that job done is if we get any of the radio companies, they have Bluetooth membership. So an ICOM, a Yaesu, whichever one wants to work with us, if we can go through them and use their membership to then ask for a profile, we could set the standard for the industry, and then all HTs could start to have that HT Bluetooth works with your cell phone, and then with the PTT on-off, you no longer have the risk of your operating system chimes whenever you get a text message or whatever comes in, that you don't rebroadcast that on your HT. Yeah, but yeah, it'll take longer for that one. I mean, I'm thanking 5-6 years horizon or more, but I'm young, so I'll stick around.
There you go.
Yeah.
I had a question from my neighbor here. So do you have the rattlegram for iOS?
So yeah, so for iOS, what it is because our friends at Apple don't make things free, and for currently Rattlegram, so I'll go back on what happened. Let's see, right there. Because it's not fully published, you need to go through TestFlight, which is when you got a beta software, it's actually a containerizer. So you install TestFlight, you click on that link again, and then you'll be able to have the beta version for iOS. In about a month, when we push Ribbit, then it's going to be on its own app store, and you won't need to use TestFlight anymore. So for the code, here is all published on GitHub. It's open source, so we published everything.
In the case you code, not
The invitation code, go back on ribbitradio.org and then click on test flight again. So the first time you click, it tells you to install test flight. Go back on the same website where I was, and then click on that link again. Click on the blue icon right there, and it's got the code here in the URL. To join the RAD Telegram beta, open the link on your phone. So just click it twice. You're not the only one telling us that. So, all right, I'll go back to the presentation quickly. I think it's another 10 minutes or so, depending on. So we covered the multipath and how we deal with the signal bouncing around and having that kind of millisecond buffer so that we can decipher. We talked about the orthogonal signals. Obviously here we represent 7 of them. We do 256. And then the technique of using 2 bytes per symbol instead of 1 byte per symbol on FSK. And then the forward error correction code. So some of the strength of Ribbit. So first, it's free as is freedom. So it's open source software. You guys can take up the code, which is very advanced, run with it, implement it in any other thing you want to do with it. It's also free as in free beer, so it's $0. We'll never ask $1 for the download. It'll stay free forever. There's no cable necessary, no TNC, no other hardware or manufacturer to buy. A good example is there's a little APRS dongle that works on Bluetooth that just, they had some supply. They sold out within the same day. I mean, that is slowing down the adoption of their mode. Here, there's no barrier for mass user adoption. I mean, people see it on YouTube, they want to download it. We're hitting around 10,000 views as of right now. Once we're not even promoting it. Once we get a good app, we'll go on the major YouTubers, the Jason and the Josh. Yeah, exactly. And then we'll have 100,000 viewers and their 100,000 downloads. So the potential is right there. And it leverages the smartphone hardware. I mean, these smartphones are so powerful, multiple gigahertz of computation right there. And for the APRS mindset people, think of this concept. Every single app is a digipeater, every app is an iGate. And that alone brings you that, mesh networking capability and that scalability. Like, there's a power outage. Okay, let's self-organize, and all of these apps starts to mesh over UHF. And it's interoperable because now you put the human as the switch gate with their device. You can have one radio on GMRS, one on MERS, one on ham, and your phone is right there. Regardless whichever one received the message, your phone will pick it up. And so very, very efficiently, you can pretty much talk to your neighborhood on FRS and have a few people, maybe the ones who need medical help, send a few messages, and then you can take that same message, transmit it over HF on a 6 meter, or if you want to have regional coverage, or you can go on VHF to the RACES Command Center, and then you resend the same message. And every time you resend the message, no transcription error, and then once a message is composed, someone can't tamper with it. You can respond to a message, so you can say, hey, I'm making an additional nota, and I'm actually correcting the information, but the original message, once you compose and you say new message, that new message can only be forwarded, can't be messed up. I mean, the content, you can't fiddle with people what they say, which is very important. And then at the bottom of it, the carriers are designed to cut through noise. Very strong forward error correction. So here I've got the new content that's never been published online. And I think you guys absorbed a lot of content, so we go pretty quickly over it. So our tech demo Rattlegram's been out for 6 months now. It's been downloaded more than 1,000 times. We've got very positive support. At one point, we had a contact form on the website. We'd receive between 5 and 12 emails per day, just saying, yeah, keep going, great. Can I have it on iOS? Can I have the source code? Very, very good, traction there. And then it works on VHF, UHF really well. It's been tested on single sideband, even with a lot of background noise because it was late in the day. And what we have now is we've stopped all efforts on Rattlegram. We stopped developing Rattlegram because it's a tech demo. Its purpose was to just show proof of concept, and it achieved beyond that. So over the last almost 2 months, we put all of our effort on the Ribbit alpha release. And what we're going to do is, I'm going to show what Ribbit does differently than Rattlegram. We need to give it at least 6 months of field tests. So all throughout this summer, we'll be in alpha. After that, we'll go into a beta. And then after that, it's going to be a 1.0. And you'll notice that there's no commitment on timelines because it's just me and Amit. So, you know, we got kids and we got full-time jobs as well. But we're going to grow the team. We're going to actually welcome mobile app developers. So the next era now is onboard some experienced mobile app developer and build a good development team. So what we've done is after 6 months, we figured out, okay, this works great. What can we do to push it beyond? So I will kind of point to the TV screen. And if you don't have questions, just takes Amit worked on that. So what we did was we kind of keeps the same center audio frequency, but we expanded the bandwidth to 2 kilohertz. So instead of being around 1.6 kilohertz so the bandwidth that you hear here right now is from 650 hertz all the way to 2,250 hertz. That's the audio spectrum. We go slightly beyond, so 25%, that gives us a little bit more breathing room, but we stay much below the filter cutoffs on single sideband. So if you look at SSB, your bandwidth about 3 kilohertz, your center frequency might be off, so you can be truncating some of the low end, and then it started to taper off at the top. So we wanted to leave enough room so that the message would go well on single sideband. And then we completely changed the carriers. So here we did a bit of a trick. So the best way I can explain it is, if you think about little dominoes, we would line them up facing towards you. So you would have 256 dominoes over time, and they would be stacked up in the time domain. So they would be narrow, but they would run for 180 milliseconds. Now you take your domino and you shift it sideways. So now they're on the lengthy side. This is the length of the domino, but they're much shorter here. If you multiply 6.25 by 180 and 31.25 by 36, it's the same total. So it's just shifting your dominoes sideways. By doing that trick, we can actually so we transmit the same RF power per symbol, but then we can stack more of them because the duration is shorter. And then that allows us to actually increase the number of bytes on the message from 170 to 256. And the second thing is, in the past, we had 33% of error correction, so your payload would be 67%. Now we have 50% error correction, so we actually increase error correction by 50. We invest more on the error correction. And then, based on that trick, the most important thing is we have 4 dB better on the background, so it should go further. On the preamble, here we invest 93% is error correction. So the payload on the symbol of the preamble, because we only need to send a few bytes to explain how the radio mode functioned later on. So we really invested a lot on the error correction on the FEC. And then here is a augmented Adamard. Keep that in mind. 1971. So that's a little bit about all the modification we've made based on the 6 months lessons learned. And then here is the first draft of the metadata structure that's going to go into the payload. So I'll go back to the screen. So in each message, we're going to have a time counter, which is an epoch that rolls over. So it's good enough to roll over after a year, which means that with a 2-second precision, we don't need to go more precise than that because the packets are a little over 1 second. So you could operate a Ribbit network offline for a year. And so after that, it's not needed because cell tower is going to be rebuilt faster than that. It would transmit the originator ID, which is either a phone number or a call sign. So why do we got phone number? Because you could have people that are not ham operators on the network. And then there's an offline counter. So this is very important because then you can know if the message comes from just somebody putting his phone on airplane mode to test the system, which is fine. Then you're gonna have a offline counter 1 to 2 days. I mean, it's non-linear, so it starts by counting the minutes and then the hours, and then it progressively rolls into days. After 57 days, it's just max out of 57. It's just you've been offline for a very long time. There's no need to go beyond that. We got grid square locator. So that grid square goes down to 10 characters. So I don't know if you've played with the Maidenhead grid square. So usually we go with 6. That's what we include in FT8. When you go to 10, the size of the grid is about the size of a home, which is enough for a first responder to find you with an ambulance. Beyond that, there's no precision need. I mean, you're like, hey, I'm here, you know. So you don't need to go, and by cutting that decimal precision, we're able to stay within, 5 bytes of data. So that's for location, and then you got the send counter. So 0 on first try, and then 255, like you can resend the message up to 255. So people who played with APRS, they have 0, 1, 2, and then that's about it. We let it go up to 255. I'm sure somebody's gonna play and try to reach 255, but at that time, then I'll make sure there's a fireworks on the screen. Here we need to keep that. So what happened is whenever the message is being retransmitted by someone else, so you start to forward the message, an incoming message, it's in your cell phone, you forward it. At that time, you're gonna input your ID, so the person who's operating that phone, and then the epoch time of when it's being retransmitted. So what happened is, you're always gonna have the origin, and then the latest retransmit. So if I go first transmission, you have 1, and then retransmit, let's say sent number 2. On the third one, you're gonna have 1 on 3, and then 1 on 4, 1 on 5. So it doesn't keep the history, but that's enough because as soon as all these phones reconnect to the internet, all of the data goes to the cloud application server, which doesn't exist yet, but that's gonna be built soon next year. And then you're gonna have the history and you're gonna be able to stitch back all of where that message is being, similar to APRS.FI. So you'll just key in from your call sign and then you'll see pum pum where it bounced. So you'll have all of that. Here's the data profile. So data profile is pretty much we explain to the app how to interpret the data that's in the payload. So if you put 0 is just plain text, and then what we're gonna have profiles for a lot of things like ICS form is gonna be one, absolutely. You're gonna have where I've been with my four-wheeler overlander type of trace of where I've been, location trace of my path. So it could be a hiker, it could be someone on a bike, or on a four-wheeler, or a light airplane, or whatever. So that'll gonna be the message profile. And then the respond to here, once you start to respond to the message, you can actually link back to the ID, which is the epoch, and this concatenated is the ID. And so then it helps the cell phone app to bring the response next to the message, the original one, so you have them grouped. You don't have to scroll 100 messages, so it groups them like emails. And then tactical hashtag, so that's for on the air events. When you have a big ham convention, they have a special hashtag. You can also use it in like overlander groups when they go out in the wilderness with their pickup trucks and go outside the cell tower coverage, they could just, put a hashtag and then all the groups and message can be found around the hashtag, so then it filters them out. And then we start to have, 209 bytes left, and that's actually greater than a text message or TikTok or legacy tweet. So all of that payload. And the benefit is that we're actually encode the text in UFT8. And UFT8 is the standard of the World Wide Web, so that means we can encode it in English, but we can also encode Japanese, Chinese, Hindu, all languages, even emojis. So what happened is by being native UFT8, if you use plain character English, you use 1 byte per character. When you start to use like some crazy emojis, some take 4 bytes per emoji or 6 bytes per emoji, depending which one you pick. But if you like use certain like non-Latin character, they'll use 2 to 3 bytes per character. So if you start typing, a lot of emojis, you're going to shrink your bytes faster. But if you're in an emergency mode, because you got the counter display, you're going to say, okay, maybe I back off the emoji for emergency message, and you go back to plain English, and then you're going to start to use really the full 200 characters. All right. And yeah. No, you regenerate because you have to append this information. Yeah, so if you record a message on YouTube, what's going to happen is that the send counter is going to stay static. But it's great transition because what happened is you got the metadata that's generated on the receive side. So on the receive side, you got the time counter when it's received, the ID who received it, and then the offline counter. So here, what you're going to see is you're going to see that message be frozen on YouTube, and it's never going to calculate the next like incremental resend. So it's going to stay frozen in whatever state it is. But when it's received many, many times over, it's going to be received at a different epoch time on the receiver side. No. I mean, it needs to work in emergency. If we start to restrict anything, somebody is going to stumble on it, and then it's going to hinder the performance in the days when they really need it. What we are looking into is we're looking at authentication. So what's going to happen is your ID, what we can do is we can actually, when we build the cloud application, is we'll actually authenticate your cell phone. So you will pretty much say, here's my cell phone. Okay, great. And then on the cloud, it's going to send you a text message on your phone to validate it's your phone. And then by doing this, the same way on Twitter, you got the validated Twitter account, you'll become validated. But in case of emergency, what happened is some people might never be able to do that validation. They're still able to go on the air. They just won't have the swoosh, checksum validated. So there's been lots of discussion on the security model. And I think the best, because if we start to make it too complex for people to sign up, then it slows down user adoption. I want people to be able to pick up the app and just say, okay, I put my call sign and my phone number, I'm good to go, and I'm up and operational. There's more chance that we kick someone out that has good intention than the other way around. So, and here at the bottom, it's still to be discussed, but we want to actually measure the quality metrics of the reception. So, like how much of the error correction was used, what was the signal to noise ratio, I mean, all of that, so that it starts to collect telemetry. And so this is like a good segue where we are today. So we've got an implementation of digital text over audio. We're still very early stage of development, even though it's been almost a year. The next step is we're going to focus a lot on the mobile app development, but for iOS as well, not just Android. We want to implement the geolocation and implement the cloud statistics. So when we start to have the statistics going, we're going to have field data of how the message were received and how much, the error correction kicked in or not, and how good the signal was. And then we can fine tune if we can go beyond what we are. And then later, this is when we're going to start to implement the FEMA form, and then the races ARIS net, they can actually start doing it on Ribbit, and it's going to help them log. So this is where I want to kind of thread with a lot of caution. So I think that's it. The demo app, I think you guys found your way. You found Rattlegram. That's our thanks. And the trivia, and then we'll talk again about Q&A, because I'm sure there's questions. So, Mariner 9's mission to Mars was the first spacecraft to orbit another planet, and that was Mars. Transmitted over 7,000 images, covering 85% of the Mars surface. By the way, the Russians were heading to Mars, and we beat them by a week or two. So we were able to launch the rocket on the launch pad in advance. Mars and Earth were aligning, and we beat them to Mars. Now, this spacecraft had the computer, you could reprogram the mission of the computer at a distance. So while it was orbiting Mars, we were able to change the mission and continue to gather data way beyond what the Russians were able to do. It was able to transmit data over a very low signal-to-noise ratio, and so they've used Hadamard for error correction. So here's the trivia. We use Hadamard as well, because if it's good enough to make the signal go from Mars all the way to Earth, with that very weak signal you can barely hear, then it's good for us to go even when the signal-to-noise ratio is really bad. We want that preamble to go through, and then the cell phone to pick it up. Yeah.
Same time?
They collide, and then you get nothing.
They collide. You can't tell the difference between them.
Right.
Okay.
But I mean, they're so short. I mean, if we would get transmission in the minutes, then you will always have this situation. But because they're so short, I mean, tactically, two messages coming at the exact same 1 second collision risk is fairly low. And then you can always pick up the HT and say, hey, resend, please. So. Yeah. So as soon as we code the cloud application, this is the stat that we want to collect on the message received. So level of forward error correction that was encoded, and quality of reception. So how much error correction was used.
So are you saying the app does that?
The app right now does none of it.
Oh.
On the reception, only the receiving app can calculate the quality metrics. But we want to start calculating them on the app and then push them to the cloud.
Okay.
Yeah. I'm going to use the Q&A slide. So how do you guys feel about it? Like, how way up? And it's happening right in Gwinnett County.
And we need to show up next week for the workshop.
Yep.
Pierre will be back, and we're going to be going over more of it.
So,
want to give a warm welcome and thank you to Pierre.